So we're on chapter 17, homework chapter. We were just introducing the idea of current. And we were saying that current is, in actuality, the flow of current is the movement of electrons in a conductor. The reality is, well, not the reality. The model we use is the flow of positive charge in the opposite direction. So if we have electrons flowing from left to right in this wire, we think of current as positive charges flowing from right to left. And what happens is, let me just draw a simple circuit here, which we've seen in our Arduinos. We have a battery, some sort of voltage source, and we have a negative side, and we have a positive side. So this would be grounded, from a Arduino perspective. So this would be GND. It would also be the negative side of the battery. And then on the positive side, we'd have 5 volts. And then we attach a resistor. And we think of the current flowing this way, going this way around. So from the positive side of the battery, the positive charges flow around here, and they go through the resistor this way, the positive charges, and then come back here. Now, what is current? What do we use as a symbol for current? Well, if it's a DC circuit, we use a capital I, so that's current. And current has units of amperes. And how does that rate to coulombs? Well, you'll find out in a second. So what we're looking at here is, how many charged particles. Now, over again, positive charge. Cross a cut into the wire. We'll just think of it as a wire. So we have this, we have, again, drawing this wire. What we do is we think of like cutting it, and you've got these positive charges which are moving, in this case from right to left, and how many of these pass this little, not actual cut, but a virtual cut. And if we counted those number of charges up, those charges would have a certain value, number of coulombs. So again, if you think of these as, electrons, each charge passing this plane in the other direction would be 1.6 times 10 to the minus 19th coulombs. And all those positive or negative charges passing this add up to a certain amount of coulombs. So how many charged particles, positive charges, cross a cut into the wire per unit time? So we're going to say it's the current is the amount of charge per unit time. So charge is measured in coulombs, and time is measured in seconds. So that means that an ampere, which is charge per unit time, is amperes. So 1 ampere is equal to 1 coulomb per second. So that's how an ampere is defined. Now sometimes you see it, current defined as change in charge per change in time. And that's a little misleading, because you think of the charge is increasing. You know, you think of delta as I'm getting more charge or I'm getting less charge. But really the delta here represents amount of charge that passes through this portion of the conductor. So delta means amount, not change. So let's write that out. In this case, delta Q means amount, not change. Okay. Now from a calculus standpoint, so if you're looking for instantaneous current, that's equal to, we'll use a small I, so I is a function of time. This is a time varying current, is going to be equal to the rate of change of the charge with respect to time. So we've seen that before, going from kind of a larger scale, delta something divided by delta something. If you take the limit as delta t goes to 0, you end up with this current is equal to this dq. And again, the dq is this small amount of charge that passes through a wire per given amount of time. So you want to think of it as flowing electrons, not accumulating electrons, but flowing electrons. Okay, so that's one question might be is how fast do the charges move through the conductor? So this is a chat window question for you. I mean, you have, unless you studied this before, you don't really have, you might not have an idea, but let's have you guess anyway. You know, is it, let's just put some, is it 1 meter per second? Is it 10 meters per second? Is it 10,000 meters per second? Is it 0.01 meters per second? You know, how fast do you think the electrons on average are moving in a wire? Yeah, it does depend. Let's assume that it's a good conductor like copper. You know, if you think about it, let's just think about this. So here's the wall, and here is a cord. So say it's a 10-foot cord, and here is the plug on the end of the cord. Okay. And here's the wall socket. So you plug this into your computer. Okay, so there's your charger, and there's your computer screen like that. And so you attach the cord to your computer, and you say, how long does it take electrons to move from here to there? How quickly? So 10,000, 10,000, yeah. Well, so it's interesting what happens here, because let me explain what's going on. Here's your conductor, and you had, they are electrons, and the electrons are not tightly bound to the conductor. That's why it's a conductor. They're not tightly bound to the molecule. So you have these electrons that are kind of wandering around randomly. So there's no current. So what happens with the electrons? They're bouncing around just from one electron to another. They have a certain amount of kinetic energy. Okay, so they're just randomly bouncing around here between the different molecules, the different metal atoms. Okay, then you apply some kind of voltage some kind of an electric field. So then what happens is the electrons start to move, and they move at a what's called the bulk velocity. And you can do a calculation. You can look it up in your book if you're interested. The calculation. It's basically looking at here's a certain amount of current. Here's the number of electrons that are free to move based on the number of atoms that are in the wire. Avogadro's number, all some chemistry stuff. And if you do that calculation, let me find the number. Like I said, you can look it up in your book, what it is. And I've got a number somewhere here. Okay. Well, actually, it's called the drift velocity, not the bulk velocity. So if you take the average speed of an electron moving in a typical circuit. And you go through the whole calculation. You find out, and it's called the drift velocity. The drift velocity, if there's no current, is zero, but the velocity of each individual electron is high because they're just bouncing randomly, but there's no net movement. It's kind of like air. If you have molecules of air, they're not just sitting there. They have kinetic energy. That's what gives you your temperature. But they're bouncing around randomly, and so there's no net movement. Now, when you have wind, then there is a net movement of 10 meters per second or 5 meters per second or whatever, 10 miles an hour, 5 miles an hour. But if you looked at the individual velocities of the molecules, it would be much higher than that. But the general movement in one direction is, whatever the wind speed is. Okay, so I know you're dying to know what the answer is. Well, it's approximately equal to 1 times 10 to the minus 4 meters per second. You're like, oh, you're full of, it can't be true. How does electricity move in a wire? If it's moving that slow, it'll take forever. If you have a 1 meter, if you have a 1 meter piece of wire, like a wire, a cord, that would be 1 divided by 1 times 10 to the minus 4. So then it would take 10,000 seconds to move 1 meter. So that doesn't kind of agree with what we think's happening. Actually, what's happening here is when you plug up whatever it is that this cable is connected to, your computer, the electrons move, some electrons move from the wall into the wire, and the electrons that are sitting right here in the wire move just a little bit slowly to the right at this speed, this really low speed. So when you plug the wire into the wall, you're not taking the electrons from the wall to the computer. What you're doing is you're pushing the electrons that are in the conductor just slightly to the right, and that's enough electrons in the wire, those excess electrons that are not excess, but the free electrons, push it through the machine, and that's what happens. So, you think of a bolt of lightning. Here's your cloud, and then the bolt of lightning goes down and hits this person, and you think of the electrons, the conductors up here, flying through the sky and hitting this guy. But actually what is happening is the electrons inside the air are all being pushed a small amount, and the electrons that actually hit the guy are probably the ones that are just near to him. So that's something to think about. It's not that important to be able to solve these problems, but it's it's counterintuitive. Okay, so that's what current is. It's a flow of how much charge passes through a given area per unit time. And what kind of currents are typical? Well, if you've taken the lab, remember there's a setting for milliamps, there's a setting for amps. So if you think about a hairdryer or something that's generating a lot of heat, that's probably in the order of a couple of amps. If you're talking about the current through the wire for the Arduino projects, it's on the order of milliamps, thousandths of an amp. How do we know how much current flows through a conductor or a resistor? Well, we use Ohm's law for that. So what Ohm's law does is it relates current, voltage, well, actually relates current and voltage for an electronic circuit. And the property that relates these two is called resistance. And luckily for us, there's a nice, for most of the things that we deal with, whether it's conductors, and a conductor like copper, aluminum, or gold, or silver, those have very low resistances. Then you have the resistors that we've been dealing with in the electronic circuits, which have higher resistances. And the relationship is, this Ohm's law says, it's a linear relationship, and it says that the current, or the voltage, is equal to the current times the resistance, or if you solve for resistance, resistance is voltage divided by current, or the third version is current equals voltage divided by resistance. So they're all the same equation. They're just one solve for voltage, one's for resistance, one's for current. This is the one that probably we have used the most in our Arduino kits. We apply a certain voltage, we have a certain resistance, we calculate what the current is. This one you could use if you wanted to measure the resistance of a resistor. If you could measure the voltage and you could measure the current, then the ratio of those two is the resistance. And, because it's a linear function, we can plot it like this. And if we use, which one are we going to use? If we use voltage and current, so current is the independent variable, voltage is the dependent variable. We draw a straight line, and the slope of this is R. We'll do that in one of our labs. We'll measure voltage and current, and then we can show that it's linear, and we can also take the slope of that line and relate that to the resistance that's measured. So let's just do a simple example here. Let me add a page. So we're going to use this one. Current is voltage divided by resistance. So, for Arduino, and we've seen this, I think he's done it. The Arduino uses resistors to limit the current for LEDs. So when you put an LED in a circuit, you could, let's just draw a circuit here. You've got 5 volts. And let's say you just put a LED in without anything else. Let's see, how does an LED look? It looks kind of like this. And it goes around like that. So If we were to put an LED in, which actually has fairly low resistance, you would get too much current flowing through here, which has two results. One is it could burn the LED out, and it doesn't immediately burn the LED out, but it would make the life of the LED lower. The other problem is if you pull too much current from the Arduino, then that can destroy the Arduino. So there's two reasons for putting a resistor in there. One is to protect the Arduino, and one is to protect the LED. Okay, so we're going to put a resistor in there, and we're going to assume that the voltage drop across the resistor is going to be 0 for right now. We're going to say let's have all the voltage drop across the resistor, just to kind of give us a limiting idea here, so we can use just 5 volts. So what is the value of the resistor that we use? Does anybody remember? What is our current for the kits that we've been using? What is this resistance here? We've used it so many times, we should remember. 330 ohms. Yeah, I think that's what it is. I think he also has like a 200 ohm resistor in the package. Let me just grab my package here. Okay, so I found my resistors. So we're looking for one there's a lot of them. So there's 220 ohms and there's 330 ohms. So you can actually use either one of those. Either one's going to work. If you use a 330, it offers a little more protection than a 220 ohm resistor. So if we measure the current is voltage divided by resistance. So we have 5 volts divided by 330 ohms, which I have to define the units for ohms here in a second, but let's just do the calculation. So you've got 5 divided by 330. And so what you end up with is 0.01515, repeating. So that is 15 times 10 to the minus 3. The reason I'm putting in 10 to the minus 3 is because that's milli. So it's about 15 milliamps. We use capital A to represent amperes. So that's the current. If you look at if you go online and search for the maximum current for an Arduino, let's see what it is. Maximum current for an Arduino Uno. It says the maximum current draw of the Arduino is 200 milliamps. It is unlikely that the Arduino itself will draw 200 milliamps. But let's assume it's higher than I thought it was. So we're only at 15 milliamps. So let's see what it says here. DC current, 40 milliamps. Okay. Oh, there you go. Actually, that is more. Makes more sense. So DC current per input-output pin. So those are the digital pins. 40 milliamps. So if we go to here, you see we got 15 milliamps. If we used a 200 ohm resistor, we'd have 200. What is 200? So we'll use the 200 ohm resistor, or 220. I guess that's the other one that we have in our kit. So if you take 5 divided by 220, you get 23 milliamps. So that's to protect us from this 40 milliamp. Now the other limit, the 200 milliamp, is for the 5 volts. So if you go between 5 volts and the ground, you can have a maximum of 200 milliamps. So if you're driving a motor, which probably is going to draw more than 40 milliamps, you wouldn't want a motor bigger than 200 that draws more than 200 milliamps. So that's pretty useful for calculating current. But we'll do a lab, like I said, we'll do a lab with an unknown resistor, and then we can look at the, I mean, you could use a multimeter to measure the resistance, but if we actually measured the current and voltage for that element, we could take the slope of that line and figure out what the resistance is. Okay, so that's Ohm's law. Units for resistance. Well, we know they're ohms, so what the heck is an ohm? So again, this is the one I remember. Voltage is current times resistance. So resistance is voltage divided by current. So we know the units for this. This is volts and amps. So the units for resistance are volts per amp. Now you could also do an ampere is coulombs per second. So this would be volts per coulomb per second, which would give you volt seconds per coulomb. That might be useful at some point. But we have a special name for this. This is called ohms. So one volt per amp is 1 ohm. Okay, so that's the units. So current is coulombs per second. Voltage is just voltage. Well, actually, no, that's not true. Volts, if you remember, where does the heck does that come from? That came from potential energy per charge. So potential energy is joules, yeah. Energy is joules, charge is coulombs. So that's volts. So let's stick that in there. So if you stick in voltage being joules per coulomb divided by coulombs, and then you multiply by seconds. So you'd end up with joules seconds per coulomb squared. I think that's right. Anyway, we don't have to worry about those things. We just need to worry that ohms are volts per amp. Yeah, so Giovanni sent a message here. So, Ohm's law doesn't actually apply to diodes or LEDs. As he says, it has a weird curve. It's almost exponential. So you almost have to take the current that, if you take the current that you would get from the resistance alone. So if we go back to this question. So if I take the current here, 15 milliamps current, you can go to a voltage versus current curve for an LED, and from that current you can calculate the delta V across the LED, which is about a half a volt, I think. So in reality, you get 4.5 volts across the resistor and about a half a volt across the LED. Let me just show you the picture here. I don't want to go into too much detail right now, but if you look at voltage versus current for diode, which the LED is a special kind of diode, you get this kind of curve. So you got voltage in the X direction, you got current, and what happens is that you have this, if you get to too high a voltage across, if you put 5 volts across the diode, pretty much it just goes crazy, you know, you get infinite current almost. So it doesn't really, that's why it burns out. But it turns out that depending upon the kind of diode you have, this operating voltage is in the range of 0.7 for silicon and 0.3 volts for germanium, and I said 0.5. So that's, but you can't use Ohm's law here for the diode because it's not linear. But you can use Ohm's law for the resistor, which would give you a little, it's kind of almost, you'd have to almost have an iterative thing here. You know, you'd figure out what the current is based on the resistance. Then once you get the current, you can calculate the voltage drop across the LED, which leaves less voltage across the resistor, and you kind of go back and forth until you reach some kind of a final solution that would satisfy both of those requirements, both the linear Ohm's law for the resistor and the other type for the diode. Okay, now what I'm going to do here is we're going to do the non-calculus version of explaining something, and then in calculus tomorrow or Thursday we're going to derive this relationship, these relationships. But I want to talk about this particular scenario because we're going to do it in lab next week. What you have is a battery, let's say 5 volts, and you have a switch. So its switch is open, and then you go through a resistor, some resistance R, and then you have a capacitor. So we're incorporating the two things we've talked about so far, resistance, capacitance. So what I'm going to try to do is here just describe qualitatively what happens when you close this switch. So we're going to close the switch. Okay, so you close the switch and you've got this battery. And what the battery is going to do is it's going to create an electric field inside the circuit. As soon as you close the switch, there's going to be an electric field inside this circuit. And so then the positive charges are going to start moving. But you can't have the charges move infinitely quickly because the resistor is going to slow things down. And I'm going to draw some graphs here versus time. And this is going to be the voltage across the resistor. I'm using a small v because it's a function of time. And I'm going to have the voltage across the capacitor as a function of time. And I can also have the voltage across the battery as a function of time. Well, that doesn't change. That's going to be 5 volts. So no matter when I close the switch, you're going to have 5 volts across the battery. Now, one thing we haven't talked about yet, but we've alluded to it, is that if you have a complete circuit here where the electrons can flow, or the positive charges can flow this way, electrons flow the other way, that the sum of the voltage drops at any instant of time, voltage drops across the resistor and the capacitor have to equal the voltage rise across the battery. It has a special name, but we won't call it yet. We'll leave it as of yet. The law with like Voldemort or whatever we don't mention. I don't know. I'm not a Harry Potter guy, so I probably screwed that up. Okay. So what happens is initially there's no charge across the capacitor because the circuit was open. Then we close it. Well, you can't instantaneously charge the capacitor. It takes time because this resistor is slowing things down. So what happens initially is, right here at t equals 0, the voltage across the resistor is exactly equal to the voltage across the battery, because you can't have any voltage drop across the capacitor unless you have some charge. But you can't have any charge instantaneously because this thing's slowing down. So the voltage across the capacitor is initially 0. Then what happens is, you start to get some charge. Some charge has been moving through here, positive charge. And actually what's happening is the positive charges are just being pushed from this wire into there. They're not going all the way around. So, but this side gets a few positive charges on it. This one gets a few negative charges. Well, when that happens, so let's say that's time A. Now there is, because there is charge on either plate, there is now a voltage. Okay, there's a voltage across the capacitor because there's now charge. There's a charge difference across the capacitor. Well, because now there's a voltage across the capacitor, the voltage drop across the resistor has to be less, because the voltage drop across the resistor plus the voltage drop across the capacitor has to equal 5 volts. So you have that at time A. Now the voltage drop across the resistor is less. Okay, then you get more charges here because you've had time for these things to move. So this becomes more charged. So we'll call that time B here. So now the voltage across the capacitor is more, and the voltage drop across the resistor is less. It's less here because there's the sum of the voltages around the circuit have to equal 0. So the more voltage drop across the capacitor, the more charge the capacitor gets, the less voltage drop across the resistor occurs. Now, once you get to some point, this capacitor is going to get fully charged. It's going to have 5 volts across the capacitor. So at that point, if I go out far enough, the voltage drop across the resistor is going to go to 0, and the voltage drop across the capacitor is going to equal 5 volts. So it's going to come out here to this voltage of the battery. So I could draw a little horizontal line, and so I'll look at some point out here, and it's going to approach that. So as the voltage drop across the resistor decreases, the voltage rise across the capacitor increases, but it's limited to 5 volts. It can't be more than 5 volts. So the question is, what do these curves look like? What is the form of the shape of these curves? We have the general idea. This is going to start at the battery voltage, and it's going to drop off, and ultimately it'll approach 0. This one's going to start at 0, and it's going to increase, and at some point it's going to approach the voltage of the battery. So here you go. Here we're going to derive these equations in calculus, but the voltage across the resistor as a function of time is equal to the voltage across the battery times 1 minus E to the minus 1 over R times C, then whole thing times T. And the voltage drop across the capacitor, or voltage drop, is going to be equal to the voltage across the battery. I got these the wrong way around. So let me make sure I'm doing this right. I may have them mixed up. Actually, this is, I do have them mixed up. This one should be this. This is the resistor. So let me copy that down, and sorry about that. This one actually is that. And what do these functions look like? So I'm going to use Desmos just to give us a general idea of what these kinds of functions have their general shape here. So if you guys who are not taking, well, even people who haven't taken calculus before, you don't have to worry about the derivation. But okay, so what we have is y equals, let's say 2, so that's the constant in front, 2 volts, e to the negative, and let's, we're just going to put negative 1/2, let's do 1/2 times t, like that. Okay. So it's an exponential decay. 2 is the starting point. Negative 1/2, you know, we just did this in our calculus test, except it was a plus, but it's exponential decay. So it starts at 2 and it exponentially decays and ultimately it'll reach 0. So if we go back to our picture here, it looks like this curve. Okay, so that's why the resistance, the voltage drop across the resistors, the battery voltage times e to the minus 1 over RCT. The question is, how do you get 1 over RC? And then we'll show you that in calculus. This one, we'll do that one as well. So let's just push enter. We'll do y equals 2 times 1 minus e to the negative 1/2 times t, like that. And there we go. Okay, so that's the blue curve. That corresponds to this one, the voltage across the capacitor. Starts at 0. It increases. Oops, wrong button. Where am I here? Oh, here we go. Yeah, so it's the voltage of the battery times 1 minus e to the minus 1 over RCT. So again, you have this negative exponent, and it fits the form that we thought it would look like. And let's actually call this Z. And then if we add another one, let's call it W. If W is equal to Y plus Z, does that work? Oh, something happened here. What happened? Why the other ones disappeared? Let me get rid of that. Anyway, what you'll find out is if you add these two, you just get a horizontal line of 2. That's the battery voltage. So they compensate each other, kind of oppositely compensate each other. Okay, now, the reason I'm doing this is I have a problem like this on the test. You just have to be able to use you have to use the equations. So let's make up a circuit. So we're going to start off with the volt, let's say 5 volts. We're going to have a resistor. We'll have a switch. Like this. We'll have a resistance of, let's say, 200 ohms. And we're going to have a capacitor. Actually, let's use a little bigger resistor, 10,000 ohms. So it's 10. Oh no, it's doing, I was afraid it was going to do my weird thing. It is. Okay. So I hadn't restarted. You know what happens when that means I've got to close the computer down. So I'm going to transfer power over here to Eric again. I'll be back in a minute or so once I get this thing. Make co-host here. Okay, so I'll see you in a second. Okay, so I was going to do 10,000 ohms here. And the capacitance will make 100 microfarads, which is going to be 100 times 10 to the minus 6 farads. So let's multiply these two things together. R times C. So that's going to be 10,000 times 100 times 10 to the minus 6th. And it turns out, if you multiply these two things together, they have units of seconds. And I get 1. How about that? So I was trying to do something like that. 1 second. So this product of the resistance times the capacitance is called the time constant. And what the time constant does is it tells us in general how quickly things occur. So our time constant is R times C. That's how you calculate it. In our case, it's 1 second. So what does that mean? Well, let's calculate voltage for the resistance at 1 second and calculate the voltage across the capacitor at 1 second. Let's see what they are. So our two equations were that the voltage across the resistor as a function of time is equal to the voltage of the battery times e to the minus 1 over RC times T. So our voltage, battery voltage was 5 volts, e to the minus 1 over 1 times T. So RC is 1 second. So that just becomes 5.0 e to the minus T. So that's for this particular case. So the voltage across the resistor at 1 second is going to be equal to 5 times e to the minus 1 power, because I plug in 1 second. So 5 times e to the minus 1 power, or 1 over e, is 1.84 volts. Now we already know what, does anybody, we can write this out. The voltage across the capacitor is equal to the voltage across the battery times 1 minus e to the minus 1 over RC T. For this particular example, it's going to be 1 minus e to the minus t, because RC is 1. And so we can then evaluate the voltage across the capacitor after 1 second. Capacitor, 1 second. You'll get 5.0 times 1 minus e to the minus 1. And you can even, the answer, because it's 5 minus 1.84. But we'll plug it into our calculator anyway, just to show it is true. So we take 5 times 1 minus e to the minus 1 power, and we get 3.16 volts. So if you take the voltage across the resistor at 1 second plus the voltage across the capacitor at 1 second, you'll get 1.84 plus 3.16, which equals 5.0 volts. So that's one of the test problems. You just plug the number in the equation. You're like, oh, that's an easy problem. And it is an easy problem, so don't blow it. And I'll pick R and C, so these numbers are not, if you pick R to be small and the capacitance to be small, then this thing drops off really quickly. And so after 1 second, this could be like 0.000 volts, 1 volt, and this could be 4.99999 volts. But I chose this particular case because it gave you a reasonable balance between the two. And it turns out this number here is 62%, I think, of 5 volts. Let's see, take 5 volts times 0.62, you'll get 3.1. So that's a key characteristic. If you know the time constant, you know how long it takes for the voltage, this voltage, to be 62% of approximately of the original voltage, and this one would be 39% of the battery voltage. So these are called RC circuits because they have a resistor and a capacitor. And it's just what we would call a transient thing, because there's a certain amount of time period where things happen, and then after a certain time, not much happens at all. This is going to level off. If I go back to my drawing here, my Desmos drawing, which I've already lost because I had to go start all over again here. But because it's of an exponential nature, things happen pretty quickly. So again, if I do y equals 5 in this case times e to the minus t, you can see that after 6, 8, 10 seconds, the voltage has almost gone to 0. It's only in that first number of time constants. If you take 1 second, which was the time constant, here's after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So after 5 seconds, the value is getting very close to 0. And what we'll do in the lab, not this one this week, but the one next week, is we will put together an RC circuit, and we'll measure the voltage across this resistor and the capacitor as a function of time. We'll choose a resistor and capacitor value so that it will take about a second to do we'll pick one that matches this example pretty closely, and we'll show how it actually works. Okay, so that is RC circuits. So now we have everything covered that's on the test, which I will put together a review. Actually, I think I already have a review from previous years, so you can watch that. I'll send it out this afternoon, and you can look at it. Okay. So what have we talked about today? We talked about how you define current. So current is the flow of electrons per unit time, has the units of amperes. I've got a question here. Let's see. When is the test? Next Monday. And it's only 5 problems long. So, but anyway, I'll tell you what's going to be on it. It's fairly straightforward. Okay, so anyway, we talked about current, then we talked about Ohm's law, which related current to voltage and resistance. Resistors follows Ohm's law, but things like diodes do not follow Ohm's law. Then we talked about this RC circuit, which is a transient. It starts off, the capacitor starts off uncharged. You close the switch, the charge starts to flow, starts to charge the capacitor. You start to get a voltage across the capacitor, which then reduces the voltage across the resistor. We're going to show how to derive these equations in calculus. But for the test, you just have to know what they are and how to plug the numbers in. The product of the resistance time and the capacitance gives us a good idea of how quickly the capacitor is going to become charged. So I think that's good. Okay, so we're going to start on this thing. I said there was a handout that if you wanted to print it out, and I'm not going to include this on the test. It's similar to what we did with with capacitors, but it's using Ohm's law instead of the definition of capacitance. So somebody asks, so is the first test in chapter 16 and 17? The answer is yes, plus what I just covered. So the RC circuits are actually in chapter 18, but I've covered that now. So yes, 16 and 17, plus the RC circuit, which is 18. Okay, so before we actually start this, we have to talk about parallel and the equations for parallel and series resistances. How do you combine those, just like we did with capacitors? So this is good practice because it's like capacitors. The procedures are the same. It's just that the equations are they're the same form, but they're actually the opposite when it comes to series and parallel. So here's series resistors before we start getting to more complicated stuff. So series again means that you have things attached end to end. USB, that's serial. That's what the S in USB stands for. Universal Serial Bus. So let's just look at the simplest case. You have two resistances, R1 and R2. You want to replace those two resistors with a single equivalent resistance. Why do you do that? For the same reason that we did with capacitors. So we can take a complicated circuit with a bunch of resistors in there and figure out what the voltages and currents are through each one of these individual resistors. And to do that, you've got to simplify the circuit. So the equation is that for series resistors, the equivalent resistance is just the sum of the two resistors. And if there's more than two, then you just add however many there are. Again, you can derive this using Ohm's law, but I'm not going to do the derivation in here. We have to compromise on something here as far as you can read it in the book, whichever book you have. It goes through the explanation, and we're kind of doing, the derivation is kind of like what we're going to be doing in the exercise. So you go through the same procedure, but with kind of just a generic, resistors. Okay, so these are resistors in parallel, and you want to replace those resistors in parallel with a single equivalent resistance. Remember, we're going for 15 extra minutes because we started 15 minutes late, so we're going to 10:45. Okay, so the equation is that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. You'll remember with capacitors, parallel capacitors, you just added them together. And for series, you did the reciprocal relationship. So they're opposite in terms of the form. Okay, so those are the equations we're going to use. So let's go look at this example. This kind of example will be on the second test. So what we have is R1 and R2 are in parallel. R3, R4, and R5 are in parallel. This one's just by itself. This is called parallel and series resistance activity. It's the one right after the capacitance one. And we have 5 volts. So the question is, ultimately, as I said earlier, how much voltage is across each one of these resistors and how much current flows through each one of the resistances. So the first step is to take these 2 parallel resistors and make them into an equivalent resistance A, and take these 3 parallel resistors and make them into equivalent resistance B. The hard part in this case is the first part, because resistors in parallel, you have to use the reciprocal relationship. So we're going to do that over here. So the equivalent resistance A, which is going to replace these two, you use the reciprocal result. Like that. So we get 1 over the equivalent resistance A is 1 over 1. So I got 1 ohm plus 1 over 2. So you add those together, you're going to get 3/2. So to get the equivalent resistance A, then you have to take the reciprocal of this, because 1 over this is that. So the answer is 2/3, and the units are ohms. So we can replace these two parallel resistors with one resistor, which is going to be 2/3 ohms. Okay, now let's do the next one. So we're going to figure out equivalent resistance B. So you guys are going to be able, you're going to do that. I'm going to set it up and then you can put it in your calculator. And again, I'm not going to, I do want the answer as a fraction if it is a fraction, but I'm going to let you cheat and use your calculators and not have to go through the whole parallel. So, you know, it's going to be 1 over, what was it here? 0.5, is that right? 0.5 ohms, yeah. So it's 1 over 0.5 plus 1 over, my memory's terrible here, 1 over 1, and then 1 over 0.25. So in the chat window, tell me what equivalent resistance, and this should be actually B. I don't know why I wrote A. Oh, this should be here. That's A. This is B. Okay. Now here's a little hint. The equivalent resistance is always lower than the smallest resistance. So here I have 1 and I have 2. So the answer is 2/3, which is smaller than the smallest. So your answer here should be less than 0.25. So if you get a number greater than 0.25, you've done something wrong. Probably you've forgotten to take the reciprocal, because what you'll get here is 7. So the answer is 1/7 ohms. Okay, so that's 1/7 ohms. Now the last one is just by itself, so we don't have to do anything there. Now now what we do is we combine equivalent resistance A or equivalent resistance B with resistor 6, which didn't change. So for this one, now they're in series. So you just add those numbers together. So let's write that down here. So equivalent resistance C is just going to be 2/3 plus 1/7 plus 1, and put that as a fraction. Go ahead and stick that in the window. You don't take the reciprocal in this case. The other the thing about series resistance is the series resistance is always bigger than the biggest. So it's got to be greater than 1, since 1's the biggest. Okay, don't forget to put it as a fraction. So wait for a few more people here. I've got 2 people. Okay, so it's 28/21 ohms. Okay, so that is my resistance. So just like we did with capacitors, we're going to go backwards now. So when we did the capacitor problem, we calculated charge. When it comes to resistor problems, we calculate the voltage, the current. So let's plug in the numbers and then see what it means. So the 5 volts from the original problem goes through the equivalent resistance. And if you, Ohm's law solved for current is I is equal to voltage over resistance. So it's going to be 5 divided by 38/21. 38/21 ohms. So we're going to do that. We're going to find the answer as a fraction here. So 5 divided by the answer, change that to a fraction. So you'll get 105 over 38 amps, which is about 3 amps, 2.7 amps. I'm just going to write the decimal number here, 2.76 amps. So let's think about what that means. Going back to the original picture here, before we actually go back. So you're going to have 2.76 amps coming here. Some of the current's going to go up, some of the current's going to go down. The two resistors, the lines come back together, there's 2.7 amps here. Then they're going to go split in 3 ways. Some of the sum of these currents have to add up to 2.7 amps. They go through each of these resistors, they come back together, it's 2.7 amps. Then the 2.7 amps go through that resistor and all the way around. So the current is the thing that stays kind of constant. The total current in here is the same as the equivalent current, and the same here. Okay, so that's the thing that when we did resistors, it was the charge that we split up. So now that we have the current, we go back one step and we calculate the voltage drops, because we know the equivalent resistances. We wrote those down, so we got to go steal those from earlier. So from this step, it was 2/3, 1/7, and 1. 2/3, 1/7, and 1. Chapter 7 homework, I think, is due Friday. 17, well, no, chapter 17 is not due until after the test, because this is not a part of the test. Okay, this is the part of the second test. The capacitors is part of the first test, but not a part of the second. So if you go back to chapter 16 here, where is it? So this is a part of the test. This is not part of the test yet. Okay. Okay, so what we have is we have the 3 equivalent resistances that we had in the intermediate step. We have the current. We know that the current through each one of these equivalent resistances is 105 over 38 amps. So because we have current and we have resistance, we can use this form of Ohm's law to calculate the voltage drops across each one of these. And they have to add up, these 3 have to add up to 5 volts, or we've done something wrong. So let's do it over here. So let's call this, we call this A, I guess, right? Equivalent resistance A, this is equivalent resistance B. Oh, I got them right down here. Okay, so equivalent resistance, the voltage across equivalent resistor B is, again, up to our equation here, it's current times resistance. So we have 105 over 38 times 2/3. So that's that one. The voltage across equivalent, that should be A, not B. I don't know why I wrote that. The voltage across B, equivalent resistance B, is the same current, 105 over 38 times 1/7. And the voltage across the 1 ohm resistor, which was resistor 6, is 105 over 38 times 1. So let's get the answers here and plug them in, and then we'll stop for today. So we got 105 divided by 38 times 2 divided by 3. Change that to a fraction. So this is 35 over 19 volts. The second one, 105 divided by 38 times 1/7. So this one was 35 over 19 volts. This one is 15 over 38 volts. So this one's 15 over 38. And then this final one is 105 over 38 volts, because you've got 1 times 105 over 38. And as a check here before we log off for the day is that these three have to add up to 5. And I probably could have simplified some of these, but no, maybe I couldn't, because, so let's add these together. 35 divided by 19 plus 15 divided by 38 plus 105 divided by 38, drum roll, 5. Okay, so that checks. So what we'll do on Friday is we will finish it off, because now what's going to happen is we have the voltages across the original resistors, and we have the resistance. So if we have voltage and we have resistance, we can calculate current, and that's the last thing. What is the current through each one of these resistors? And then we're done. Did we do the calculated electric field for voltage hedge? That actually is a calculus-based problem, so you don't have to do that one for non-calculus based students. There's nothing to hand in today, because we're going to you'll hand this in when we finish it on Friday. The other stuff I did was not a handout. Anybody got any else questions? So the review for next Monday's test will come out today. You can look it over. If you have any questions, let me know. And I think that's it.